Welcome to Friday. Today I'm just going to quickly go over what we talked about yesterday and how you can complete the practice problems with radiometric dating. So just a reminder from yesterday that we learned about basic atomic structure, proton, neutron, electron, the three things that make up elements, and that the atomic number and mass really have to do with the number of protons, which define the element, and the mass is protons plus neutrons. And the strong force is that invisible force that keeps all of these positive protons that ought to repel each other together in the nucleus. Now, that strong force is sometimes overwhelmed when the quote-unquote VIP clubs, the nucleuses, get too many peeps in the club. And when you're a VIP club and there's too many people, it doesn't become exclusive anymore. It becomes a little bit strained because everyone's vying for that space. So we need to kick out those extra people to reassert the exclusivity of the VIP club. So when we look at isotopes, maybe carbon-12, carbon-13, carbon-14, carbon-13 and carbon-14 are radioactive because they have those extra neutrons, which makes their nuclei unstable. So radioactive events are when these unstable isotopes, which we often call parent nucleuses, kick out some extra protons and neutrons to become a stable daughter nucleus. Now, this discharge is constant for each specific type of element, which allows us to be able to date things, but also it gives us a really good idea of when we look at things with any type of radioactive isotopes, we can compare the amount of parent to daughter, and that will give us some really good information about its relative age. Which brings us to radiometric dating. So each radioactive isotope has a half-life, which is basically the defined period in time in which 50% of the VIP clubs are going to kick those extra peeps out to become stable. Now, over time, this means the amount of radioactive material diminishes by 50% every half-life. So we tend to go from 100 to 50 and 50 to 25. But in between those time intervals, we're still losing radioactive material. It's just that it doesn't fall neatly on a half-life sort of duration, which is why we have this Google Sheet, which allows us to measure different radioactive and stable isotopes with different half-lives to age things with different ages. So we have two problems that I have up on the board just to help you think about how you can finish your practice problems today. The first is where we're going to be converting time into mass. I know the age. What is the mass? And the other is where I'm going to be converting mass into age. So a woolly mammoth bone has a mass of 1,000 grams. 1% of it is carbon-14. How many grams of carbon-14 would be left after 100,000 years? I'm sorry, that was Mr. C. He wanted to say hi. So I'm going to put in my initial mass of 10 right here under the carbon-14 Google Sheet, because again, each of these isotopes have a different half-life. Put in 100,000 years, and notice that I have a meager 500,000th grams, less than a grain of salt of carbon-14 left. Well, about 9.9999 grams of that initial carbon-14 has become stabilized into nitrogen-14. So carbon-14 is really only good at dating things for about 30 to 40,000 years, and afterwards it becomes incredibly hard to find the carbon-14 in the material. It's sort of like Where's Waldo? Now, the other thing that I can do is convert my mass into time. So I have uranium-235 in a rock. The current measurement is 3.4 grams of the radioactive isotope and 7 grams of the daughter isotope, which brings me to a grand total of 10.4. You will have to do some addition here. And that leaves me with 30 to 33% of the mass being radioactive. That should make sense intuitively, because if 10.4 was 5.2 and 5.2, I would be at exactly 50% of my mass being radioactive, which is one exact half-life. So if I make this less than 5.2, suddenly I've decreased the amount of radioactive isotopes, which means that the years have gone past that 710 threshold and at 1.14 billion years old. So for today, I want you to wrap up in your M&M radiometric dating activity these 3 questions as best you can, and to also make sure that you've submitted your rock lab. Have a great Friday, get outside, enjoy the sun, and hope for a little bit of rain.